Today we have Zoraida Rico. She's a postdoc at Columbia University. Before she was a PhD student of Roberto, and she's going to talk today about fine bounds on covariance estimation.
Thank you very much. It's a pleasure to be here. Thank you for the invitation. So today I'm going to tell you some things about covariance matrix estimation. This is a research, a result that belongs to a research line that tries to estimate mean and covariances with the best possible not asymptotic performance. And it's based on a joint work with Roberto. So let's start with the, in some sense, the scalar version of this problem. The simplest problem in statistics is estimating the mean of IID real random variables. So with a common probability distribution P, so we want to estimate the mean that is unknown. How can we use the information that we have of the sample in order to estimate the mean? So an obvious answer of this question is to use the empirical mean. This is obvious because of the lab of large numbers that tell us that no matter what the underlying probability distribution is, we can, the empirical mean or the sample mean will converge to the mean estimator when n's go to infinity. So it's a consistent estimator. Also, we can solve this problem with an algorithm of order n. However, here the rate of conversions could be arbitrarily slow. So we are going to assume a second moment. Our question is going to be given a delta between 0 and 1. That's the error that we allow. What is the smallest accuracy that we can guarantee? So the central limit theorem implies that we can achieve this bound when n's go to infinity. And we would like similar inequalities in a non-asymptotic setting. So this we're going to call sub-Gaussian error bound, and actually it's optimal. It has been proven in 2016 by Debrois, Lugosi, Oliveira, and Nerals that no matter what estimator you have, there's going to be a distribution such that the error bound is going to be at least of this order. So can we find, so what happens if we continue using the sample mean estimator? Actually, it has been proved by Catoni in 2012 that the Chebyshev inequality is essentially tight for some kind of distribution. So if the distribution is not sub-Gaussian, we only have this Chebyshev inequality. Here we have the optimal rates on the deviation as on n, but this, well, the dependence on delta is not necessarily good if we want to estimate several means. So can we obtain better estimators? And the answer is yes. A breakthrough in the area. What's the introduction of the median of means? If we just have a mean and a variance, then it has been proved that actually the median of mean estimator is sub-Gaussian. What is this estimator about? You have the observation. You divide the sample in k blocks. And then you compute of size m, then you compute the empirical mean in each block, and then you take the median. So there is a lot of recent work and also a lot of work in this area in general. And the situation of the median of mean is like there is, even in the high dimensional scenario, there are efficient sub-Gaussian estimators, in some sense optimal. And also we can achieve the efficient algorithms. But the situation of the covariance, that is what I want to talk about now, later, is not as good as the estimation of mean of vectors, of the estimation of the mean if we consider the median of means. So let's make the problem a bit more harder. There's going to be an adversary that inspects the sample and arbitrarily modify a fraction eta of the observation. So now we're going to look to y1 to yn, and we want to recover the covariance matrix of the original sample. So, okay, a natural estimator in this sense, like the three-mean estimator, is the oldest estimator in robust statistics. Actually, the idea, the notion, it's quite old. There is an example here that in the fragment, this is a fragment of the fourth book of the history of the Peloponnesian War by Thucydides. So in the century 4 before Christ, there is a story that actually it has the notion of the three mean, like he was a general in order to rescue some prisoners, actually used this notion. So this is what is the three means? It's like a natural choice if you have robust, if you want an estimator that is robust. So you remove the k largest and the k smallest points of your sample, and then you take the empirical mean of the rest. The explicit definition appeared on 2K in the 60s. Then Uber in the 70s related the trend mean to the robust statistics. In the 70s and in the beginning of the 80s, there is a lot of work on the non-asymptotic setting, like what is the parameter, the correct parameter of the trend parameter for in this scenario, in the asymptotic, for have asymptotic optimal error bounds. So actually, the first result, that proves that the trend mean estimator is a sub-Gaussian estimator, is recently. This is a work with Roberto and Paulo that we hope is going to be soon in arXiv. And one of the observations is that if we have the mean and the variance, and also we have to other bounded moments, then we obtain the sub-Gaussian error bound and also the min-max optimal bound for the contamination. That if we consider p equal to 2 is going to be square root of eta. Here this epsilon is eta. For higher dimensions, you can see Lugosi and Mendelssohn. There is also a result by Oliveira and Resende that analyze in more abstract sense the trend mean estimator and recover this result, but they cannot recover the next error bounds of the problem I want to talk about today. That is the covariance matrix estimation. So this is an important problem in high dimensional statistics and has regained a lot of attention in the past decade. It has applications for principal component analysis, linear regression. So let's see what is this problem about. So given x1 to xn IID real random vectors with a common probability distribution, we want to estimate the covariance. So our goal is to find a random element such that the deviation of this random element and the covariance in the operator norm is small with high probability. So I'm going to tell you what small means in this context. But before again, like a natural estimator for this problem is going to be the sample covariance. And the study of the sample covariance comes from an asymptotic study and non-asymptotic studies, and they were trying to see what is the optimal dependence on the dimension. So we have in the asymptotic studies, the theorem by Yin in 93, that if we have x1 to xn independent 0 copies of a random vector with a unit, with the covariance of the identity, then if the coordinates are IID, if we just assume a 4 bounded moment, then we achieve this asymptotic convergence rate almost surely when the d and n's go to infinity and d over n converge to a, that is between 0 and 1. Then non-asymptotic studies started in the 97 by Kanan, Lovash, and Simonovich, when they were trying to study to estimate the volume of a convex body. And the first optimal result, it comes in 2019. They assume x1 and xn independent for the family of sub-Gaussian vectors. And then if they is less or equal than n, they achieve the optimal bound with high probability. So what happens if we have, if we want more general probability distribution families? So what do we have beyond the sub-Gaussian case? So this result is amazing by Trihomirov. He proved the optimal rate of convergence, square root d over n, and just assuming the bounded p moments for p greater than 4. Soon the literature moved, and they wanted bounds that not depend on the dimension, rather on the effective rank of the covariance matrix. That sees the trace of the covariance over the operator norm. This is between 1 and d. And what do we have here, like dimension-free results? We have the work by Kolchinsky and Lunici, that they prove that if we assume a Gaussian family of distributions, then they achieve the sample covariance in the Gaussian case. So this is what is going to be optimal for us now. So there is 2 questions now. The first one, what can we achieve by going beyond sub-Gaussianity and in the free dimension setting? And then Chen, Gao, and Ren, they observe that even if you have a distribution of Gaussian families, it's just, if there is just one point that is corrupted, then the performance of the sample covariance is compromised. So, well, the only assumption that we are going to have is the LP-L2 hypercontractivity. This tells us that if the higher moments of the one-dimensional marginals are bounded by the second moment. This assumption allows to a vast family of probability distributions. For instance, if we consider the L sub-Gaussian distributions for p equal 4 and we take kappa equal to 2L, it belongs to this class. Also the test student with large enough grades of freedom, and the sub-exponential families of distribution with band of norm. Well, so our question now is if can we design an estimator for the covariance based on the model of contamination, and if we only have this hypercontractivity assumption for p greater or equal than 4. So let's see what we have. We have results by Minsker that in the problem of mean estimation of random matrices in general norms. But this work loses by logarithm factors. Then there is Catoni, and Giulini, the mean estimation of matrices. But this approach requires previous knowledge of certain parameters of the problem, such as the kappa p. So the state of art, the best published result, is to Mendelssohn and Shivotowski. This is for eta equals 0, so there is no contamination. And they design an estimator such that if the sample size is greater than this quantity, achieve this bound. But this is different as the bound that we want, like the Kolchinsky and Lunici, because there is a log factor, an extra log factors in the sample size and also in the convergence rate. With some techniques, new techniques, we can remove these log factors using this estimator. But the thing is that if we consider eta between greater than 0, in the scenario of contamination, since this approach is based on a median of mean estimator, we cannot recover the optimal eta. We recover something like eta instead of the square root of eta. There is also a parallel work by Abdallah and Chibotrovsky. What they did is like a kind of version of Bayes' theorem in a non-asymptotic setting, and that does not depend on the dimension, but with the hypercontractivity assumption. This is an open problem to try to solve, like in the theorem of Bayes for p equal to 4. And they use an estimator that is based like in a soft truncation. So the main result is that if we fix a delta and a contamination level, then there is an estimator such that if we have the hypercontractivity assumption, we recover, and for n greater than the effective rank plus log 1 over delta, we have the sub-Gaussian bounds. So let's see a little bit of these terms. The first one is the same for p equal 4 moments as in the Gaussian case. The second one, the dependence on the contamination level at eta is min-max optimal, the square root of eta, when p is equal to 4. In the sub-Gaussian case, is eta log 1 over eta, with the kappa of further square root of p and p large. This could be better. Actually, it was recently proved by Shivotrovsky and Minassian, the optimal bound for the sub-Gaussian case. Also, our techniques can be extended to lower values of p. So if we consider the hypercontractivity condition for LK L2, for LQ L2, for Q between 2 and 4, we have this error bound. In the case of 4, it's the optimal one, but it's not as good for if we have less moment assumptions. So what are the key ideas of the proof? We're going to consider a type of mean estimator. So the fundamental problem in higher dimension is that there is not a definition of a median of means or the mean estimator that work in the case of the real line. So we're going to base on a mean estimator, and then we're going to show that actually the trimming process could be approximated by a truncated process. And then we're going to use back-Bayesian techniques to control this truncated empirical process. So if we want to estimate the covariance, it's equivalent to estimate the inner product of all the vectors in the d-dimensional sphere, covariance and the vector. And now we're going to consider for this the mean estimator given as follows. So we're going to take the infimum of all the index sets of size n minus k of the sums in this index set of the inner product, square inner product of our contaminated sample over n minus k. So we have an observation here that actually we can find a random element that works for every k. We're going to have a random element that is going to be as this. And also, in addition, the deviation of this random element and the covariance in the operator norm here is going to be less or equal than this process, that is trimming process. So this talk is not about the algorithm aspects of the problem. Like clearly here, if we consider this estimator, this is not optimal. We can reformulate this instead of looking in all the sphere. We can look in a 1/4 net of the sphere. And then in the last line, we are going to have a problem of solve a convex function. But it's going to be exponential in the dimension of the space. So this is not computation. Okay, so what we want now is control this trimming process. So what we do now is we're going to have this deterministic result that under a counting condition, like if in all the unit sphere, the points such that the square inner product is greater than b, is less than t, we have the following approximation. We can approximate the trim process as a truncated empirical process. So at a high level, what we want to do is we want to bound the suprema of two empirical process. If we have this, what we have to do, what the tools that we have to solve problems like this, we have a random process over a set of parameters. So if we want to analyze the soup of this, we can use the chaining strategy for that this arises as a way to understand the relationship between the supremum of the random process and the geometry of the set of parameters. So by performing discretizations in this set and controlling the increments, z theta 1, z theta w. So if we can guarantee that this difference, the probability that this difference is large is small, then we can use the chaining strategy that was used by Kolczynski and Luminici to remove the dimension in their proof. However, they consider that the family of distributions were Gaussian, right? And they have a good control here. But for the hypercontractivity condition, we don't have that. So we cannot use this. Other thing that we can do is use inequalities for matrices. So in this sense, this was, but the price we pay for use this kind of concentration inequalities is the log factor, as in Mendelssohn and Shivotowski, and we don't know how to avoid that, even if we use like more sharp concentrations like the last work of Van Handel and Tanya. So what we're going to do instead is, instead of look at this random process, we are going to look at an average version of this process. And there you're going to have. So we're going to look at this, where this M is going to be a suitable family of distributions over the parameter set. So now we're going to, the core of this proof is that we develop kind of Bernstein type inequality for the empirical process. So if we want to control this, with the, here the mu is going to be the Gaussian measure there as a capital gamma. That is the Gaussian probability distribution with mean V and covariance matrix gamma identity. Then in order to control the supremum of this, we're going to need just bound the general generated moment of the of z theta at one point, and also we're going to have to pay a price that comes from the Kullback-Leibler divergence in this set M. And this is what this lemma is telling us. So under this assumption, so this works for independent and bounded second moment families of random variables. If we consider the Gaussian measure here, mu, we're going to have this. So now we can control the supremum of a smooth version of the empirical process and by quantities that we know how to control. So how do we use this in our problem? What we want to do is to analyze this counting condition. So actually, if we pick B, this B equal to this BPT in this sense, then we're going to have that the counting condition holds with high probability. And here we consider this Z Y equal to the indicator of X, Y, and V greater than B. And we can apply the Bernstein type inequality. As the process, the truncated empirical process, we have to control. So actually, this epsilon B and smoothed version of the empirical process are the deviation between these two is small. This proof is quite technical, so I'm going to skip it. So what we need now is to control this smooth version, but we know how to do this with the packed Bayesian bound. Sorry, here is something like this. And so now we're going to put everything together and we're going to show that the estimator is good for a range of values of K's of this form. So what is the problem here is that we don't know the effective rank. But what we can do is to estimate effective rank. So we win the game by finding a K of this form, for which we need to have an estimator. So we're going to estimate the trace and the norm. For estimating the trace, the problem is estimate the mean of positive real random variables. We know how to do this. We can use the trim mean estimator presented before. Or since we have this packed Bayesian lemma, we can use an estimator of this form, like the infimum of the index set S of size n minus k, and this sum of the square norm of y a. And then it follows that with the probability 1 minus delta half, we're going to have an estimator for the trace. And using the things that we have until now, but considering k as a fraction of n, we also can estimate the operator norm. So now we have an estimator for the effective rank. And then finally, we said that the K that we choose is going to be of this form that depends on the level of contamination, also the estimative of the effective rank, and log 1, this is log 1 over delta, and this is a constant times this, all this. So our final choice of the estimator is as following. We're going to consider the E star hat as the E hat, K hat of this form. And what are the open problems? So is there a computational efficient covariance estimator with similar properties? Actually, the literature is far to understand this problem, and it's an interesting problem. Okay. Also, is it possible to avoid the hypercontractivity LP-L2 condition for p greater or equal than 4? And that's it. Thank you. Do you have any questions?